Hey everyone, welcome to this explainer. I'm absolutely thrilled to have you here today because, well, we're going to look at something truly fascinating. You know, when you look out the window of a commercial airliner, you see those massive wings, the giant engines, and you probably marvel at the aerodynamics of the whole shebang. But today, we're focusing on the invisible heroes of aviation. We're talking about the highly engineered hydraulic fluids that literally keep these 300-ton metal birds in the air. We're pulling directly from the ME 3531 Aircraft Systems module to demystify exactly what's pumping through the veins of these incredible machines.
I want to immediately anchor our conversation to this number right here, negative 54 degrees Celsius. Think about the most bitterly cold winter day you've ever experienced. Got it? Well, it doesn't even come close to this. This is the extreme, high-stakes freezing temperature that an aircraft faces when it hits a cruising altitude of 35,000 feet. If the liquid pumping through the aircraft's control systems freezes solid at this temp, well, no way around it. The pilot can't move the flaps, the landing gear won't deploy, and the aircraft just cannot be controlled. This number is literally the ultimate adversary for aviation engineers.
Okay, let's dive into this. Here's our roadmap for demystifying these highly engineered liquids today. We'll cover the functions of aircraft fluids, surviving extreme altitudes, the viscosity factor, managing fire and heat, types of hydraulic fluids, and finally, handling fluids safely.
All right, starting off with Section 1, Functions of Aircraft Fluids. Let's see why they're so dynamic and crucial. So, first things first, we have to completely shift our perspective. We aren't just talking about some passive liquid sloshing around in a tank. No, this engineered fluid serves a vital triple-threat role. First up, it transmits power. Think of it as the aircraft's muscles. When the pilot pulls a lever, this fluid instantly transfers that mechanical force all the way across the plane to move those heavy control surfaces. Second, it acts as the aircraft's joints, constantly lubricating moving parts so you don't get that awful metal-on-metal grinding. And third, it's a radiator. Pumping fluid at these crazy high pressures generates a ton of friction, so the fluid itself actually has to cool and dissipate heat away from the really critical components.
Moving right along to Section 2, Surviving Extreme Altitudes.
So, imagine this. A single drop of hydraulic fluid goes on a seriously intense journey every flight. Down on the ground, it might be sitting at a nice balmy 15 degrees Celsius. But just minutes after takeoff, the aircraft is climbing rapidly. As it passes an altitude equivalent to Mount Everest, around 29,000 feet, the outside temperature plunges to negative 42.5 degrees Celsius. And then, as it reaches its final cruising altitude of 35,000 feet, bam, we hit that bone-chilling negative 54 degrees. The fluid trapped inside the unheated parts of the wing, it has to perform flawlessly across this massive, rapid temperature swing. No pressure, right?
Which brings us to Section 3. The viscosity factor, and dealing with internal resistance.
To actually survive these freezing extremes without turning into a solid block, we have to talk about viscosity. Simply put, that's the internal resistance of a fluid to flow. Think about honey. It has high viscosity, meaning a high internal resistance, so it drips and flows super slowly. Now compare that to water, which has a much lower viscosity and just pours right out. If a hydraulic fluid gets too cold, it thickens up, just like honey. And as you can probably guess, if your aircraft's fluid flows as slowly as honey at 35,000 feet, your flight controls become dangerously sluggish. Definitely not what you want mid-flight.
And this brilliantly illustrates how engineers solve this exact problem. They use something called the viscosity index, or VI, which maps out the relationship between viscosity and temperature. A low viscosity index, which you can see by a steeper slope, means the fluid thickens up rapidly in the cold. But a high viscosity index means there's way less of that dangerous thickening when temperatures drop. So for aviation, engineers literally must design fluids with incredibly high viscosity indexes, ensuring the fluid keeps flowing like water, even when it's negative 54 degrees outside.
Okay, Section 4, Managing Fire and Heat. Let's look at chemical stability. Freezing is really only half the battle, though. We also absolutely have to manage chemical stability to prevent aviation fires. When you're dealing with highly pressurized oils sitting right next to incredibly hot jet engines, we kind of have to split hairs on two critical technical definitions, flash point and fire point. The flash point is the temperature where a liquid gives off enough vapor to ignite momentarily if a flame is applied. Basically, it flashes and then goes out. But the fire point, that's the temperature where it gives off enough vapor to ignite and actually continue to burn.
In the terrifying event of a hydraulic leak near a hot component, having a fluid with a very high fire point is absolutely essential. It's the literal difference between a quick, momentary flash and a sustained, catastrophic airborne disaster.
Next up, Section 5, Types of Hydraulic Fluids. What are the actual chemical solutions here? Looking at the specific chemical solutions used in modern aviation to combat these extreme threats, we start with mineral-based fluids. These are processed from petroleum. They work well, for sure, but they're generally restricted to systems where the fire hazard is pretty low. Next, we have polyalpha-olefin-based fluids. Try saying that 5 times fast. These offer much better fire resistance than mineral fluids, but they have a distinct flaw. When operating at really low temperatures, their viscosity increases just a bit too much. Finally, we arrive at phosphate ester-based fluid. Because it is extremely fire-resistant and holds its viscosity across vast temperature ranges, phosphate ester is the undisputed king. It's the absolute standard for commercial aircraft today.
Let's transition to our final section, number 6, handling fluids safely.
Now, we need to slow down a bit here, because that incredible chemical performance, it comes with a dark side. There is a heavy human cost for ground crews. Take a look at this. A dangerous hydraulic fluid leak on the tarmac leaves heavy staining on the aircraft wing. When a maintenance tech goes in to fix that defective component, they are coming face to face with an incredibly aggressive chemical compound.
So, the crucial point is this. Phosphate ester is phenomenal at resisting fire, but it is highly toxic to human biology. Prolonged exposure to this fluid actually dissolves the fatty materials right out of human skin, causing severe drying and tissue damage. Because of this, ground crews have to operate under super strict personal protective equipment protocols. Mechanics must wear specially rated gloves, total eye protection, and often they require specific respirators just to even be in the vicinity of the vapor. It's serious stuff.
And I want to leave you with this final, provocative thought directly from our source material. Despite the heavy-duty gloves, the respirators, the high-viscosity indexes, and all that advanced phosphate ester chemistry, the engineering document features this really sobering, handwritten warning. All hydraulic fluid can catch fire in right condition. It's a stark reminder that no matter how advanced our technology gets, flying a 300-ton machine at 35,000 feet will always carry inherent risks. So the ultimate question is, as aircraft fly higher, faster, and longer, how far will we have to push chemical engineering next just to keep the impossible routine? Thanks so much for exploring this with me today.